This is section 7.2, radioactive decays. We're going to talk about three types of decays: alpha, beta positive and beta negative, and gamma decays. Also, we're going to talk about another type of transmutation, which is electron capture. Radioactivity is a process by which the nucleus of the atom spontaneously disintegrates. Ernest Rutherford used high-energy particles to bombard the nitrogen and discovered that oxygen was produced. The nuclear fission is a decomposition of a large or split of large unstable nuclei into a smaller, more stable nuclei. New element is always formed. What is the difference between a chemical reaction and nuclear reaction? A chemical reaction is the interaction of substances to form new substances. The initial substances may be elements or compound. They are called reactant. The substances present at the end of the reaction, a chemical reaction, which also may be elements or compounds, are called products. In a chemical reaction, the entities do not change. All of the entities that were present in the reactant are present in the product. For example, in a balanced chemical reaction clearly show that carbon and oxygen are entering the chemical reaction, and carbon and oxygen are product of the chemical reaction, but in the form of compound, which is a carbon dioxide. But you clearly see there's a carbon before and carbon after, and oxygen before and oxygen after. In a nuclear reaction, a new element is formed that is absolutely totally different from what enters in the nuclear reaction. Nuclear reaction is a process by which the nucleus of atom sometimes changes. The idea of the element is determined by examining the number of protons in its nucleus. So I said the passport of element is number of protons. If the number of protons changes, one or more new elements are formed. For example, uranium, if it is bombarded by a neutron, then the barium and krypton, totally two new elements, are formed. So this is a difference between nuclear reaction and chemical reaction. In a nucleus of element, it is very interesting to see that the effect of two forces, electrostatic force and strong nuclear force. The electrostatic force is a force of attraction or repulsion due to the electric charges. So we know that based on electrostatic law, unlike charges attract and same charges repel. And we're focused on the two positive charges. So they repel. And we know that in a nucleus, we have positive charge particles and we have neutral charge, no charge particles. So since the nucleus is made with a positively charged, shouldn't they push each other, disintegrate the nucleus? But nucleus is not really easily disintegrated. Actually, it is very strong formed. It is very hard to break the nucleus of the element. So strong nuclear force is always attractive and help to hold together the neutrons and protons in the nucleus of the atom. So strong nuclear force is much stronger than electrostatic force and is responsible only for holding the nucleus of the atom together. So if you see, there are force of repulsion between protons, but in that range, the strong nuclear force, which is really much stronger than electrostatic force, will keep that nucleus together. Although strong nuclear force keep the nucleus together, Atoms with a higher atomic number, so more protons, so more charges, experience a greater electrostatic force of repulsion among protons, and the protons became more separated. Electrostatic forces are great enough to overcome a strong nuclear force, and nucleus spontaneously disintegrates and releases the energy. Radioactive decay is a process by which a radioactive atom's nucleus disintegrates, breaks apart, and forms a different atoms. So new elements are formed. There are three common forms of radioactive decays. Two of them, new element is formed, and other one is just a release of extra energy after one of those decays. Alpha, beta, and gamma, there are three letters of Greek alphabet. Alpha decay, beta decay, gamma decay. So it's easy to remember. Alpha decay is a nuclear reaction in which an alpha particle is emitted. In alpha decay, a helium nucleus consisting of 2 protons and 2 neutrons is spontaneously emitted from the nucleus. A new element is formed. Here is a plutonium-240 that undergoes alpha decay, and new element is formed as uranium-236. So nuclear reaction of this alpha decay is plutonium-240 undergoes alpha decay, uranium-236 is formed, and alpha particle is emitted. Here is a diagram. Plutonium-240 and alpha particle, which is a helium nucleus, is emitted while the new element uranium-236 is formed. Helium-4 nucleus is called an alpha particle. When a substance undergoes alpha decay, the mass number A is reduced by 4. So that means it's 2 protons and 2 neutrons. That is part of helium-4 or alpha particle. And atomic number is reduced by 2 because there are 2 protons in that particle for the same reason. This is a generic equation. So parent element, we call it as X with an atomic number Z and atomic mass A, undergoes alpha decay. A daughter element, we call it Y, is equal A minus 4, so mass is reduced by 4, and atomic number Z is reduced by 2, plus the helium nucleus is emitted or alpha particle is emitted. The atomic number changes during the alpha decay, so the new element is formed. The nuclear reaction is said to be a transmutation. So transmutation is a nuclear reaction that produces a new element. In a nuclear reaction, the parent atom X is a reactant atom, and a daughter atom Y is a product atom. Here is a uranium-238 into a thorium-234. So that alpha decay, new element is formed, and from uranium-238, thorium-234, the mass is reduced by 4, that goes to an alpha particle, and atomic number is reduced by 2. So from 92 goes to 90, new element is formed, and here is the alpha decay nuclear reaction. So uranium-238 is reduced by 4 in a thorium-234, and atomic number from 92 to 90, and alpha particle is emitted. Here are a couple of examples with alpha decay. Determine the element that is produced when lead-204 undergoes alpha decay, and write the generic and nuclear reaction equation. Let's start with the generic one. So it's XAZ with atomic mass A and atomic number Z undergoes alpha decay, and a daughter element is formed with a mass 4 reduced and atomic number reduced by 2, and alpha is emitted in form of helium nucleus. So we started with a lead 204, and atomic number of the lead is 82. So helium is emitted, so mass has to reduce by 4. From 204 minus 4 is 200, and from 82 minus 2 is reduced to 80. You go to a periodic table and look at the element that has atomic number as 80, which is mercury, and atomic mass of the mercury is 200, so we can say isotope of mercury 200 is produced. Determine the element that is produced when a plutonium-239 undergoes alpha decay. Write the generic and nuclear reaction equation. Let's start with the generic. Generic is the same as before, and then we start off with plutonium-239, and alpha particle is emitted. So we have to reduce mass by 4. 239 minus 4 is 235, and atomic number by 2. From 94 minus 2 is 92, and we can look what is 92 is a uranium, and uranium-235 is a isotope that is produced. Beta decay is a type of nuclear decay reaction that involves emission or capture of beta particle. The beta particle, the high energy electron with a negative charge, or a positron with a positive charge, ejected or captured by a nucleus. A positron is a particle with a positive charge and the same mass as an electron, so considered as a massless. There are two types of beta decay, beta positive and beta negative. Electron capture is a special form of nuclear transmutation when there's no radiation, but new element is formed. That's why it's called nuclear transmutation. In the beta negative decay reaction, an electron is emitted from the nucleus of the parent atom. When a nucleus contains too many neutrons, the neutron spontaneously decays into a proton and electron. Proton remains and electron is ejected from nucleus. This process is a transmutation because a different type of element is formed when a neutron in a nucleus of the parent atom changes into a proton. So mass remains the same because the element is ejecting or emitting a beta-like or electron-like emission, which is a massless. However, atomic number increased by 1. Here is a generic equation for beta negative decay. So parent element with atomic mass A and atomic number Z undergoes beta negative decay, which one charge is emitted. That means the new element is formed with the same atomic mass, but with an extra proton. That means atomic number is +1. An example of beta negative decay reaction is a decay of the tritium or hydrogen 3 into a helium 3. The equation for this reaction is, so the parent element with atomic mass A and atomic number Z undergoes beta negative decay when a new element is formed with an atomic number +1 while the mass remains the same. So helium is produced because helium had atomic number 2 while the mass will stay the same as 3. So here's a diagram. When in hydrogen 3 we have 2 protons and 2 neutrons and 1 proton, and one of those neutrons become a proton emitting an electron and forming a helium that has 2 protons. So identity of that element is changed because number of protons changes. A typical example of the beta negative is a carbon 14 to a nitrogen 14, which is a carbon dating. We're going to talk about this later on. But here is a diagram. So carbon 14 undergoes a beta negative decay when a nitrogen 14 is formed. In the beta positive decay reaction, a positron is emitted from the nucleus of the parent atom. So that means an electron-like particle, but with a positive charge. When nucleus contains too many protons, a proton spontaneously decays into a neutron and positron, and the positron is ejected from nucleus. This process is a transmutation because a different type of element is formed when a proton in the nucleus of the parent changes into neutron. The mass number of the daughter element remain unchanged because positron, the same as an electron, is considered as a massless, but atomic number decreases because positive charge is extracted, is ejected with a positron that is ejected from a nucleus. So generic equation for beta positive decay is a parent element with the atomic number Z and atomic mass A undergoes a beta positive when a mass will not change, but atomic number will decrease by 1. An example of beta positive decay reaction is a decay of carbon 11 to a boron 11. The equation for this reaction is X as a parent element with a AZ atomic mass and atomic number undergoes beta positive decay. So an electron-like particle, which is with a positive charge, is emitted. It's a massless like an electron, but the charge is +1 instead of -1 as electron. That's why it's called positron. And a daughter element with the same mass is formed, but with the atomic number -1 is reduced by 1. So carbon atomic number is 6 and boron is -1, 5. So here is what happened. Boron 11 is formed, and we know that this is a diagram with one of those protons in a carbon is turned into a neutron. That's why we have 6 neutrons instead of 5, but we have 5 protons instead of 6 because one positive charge unit is already ejected in form of positron. When we talk about beta positive and beta negative, we saw only a simplified version of the real beta decay. So real beta decay, we are going to learn on particle physics. It is associated with the antineutrino for beta negative decay and neutrino with a positive decay to balance that energy that is released. So antineutrinos and neutrinos will carry that extra energy that beta positive and beta negative decay will emit. In the electron capture, no particle is emitted from the nucleus of the parent atom. This process is a special form of transmutation because a different type of element is formed. So a new element is formed when an electron is captured or absorbed by a proton in a nucleus of the parent atom and changes into a neutron. So proton with a positive charge is neutralized by a negative charge of the electron and together form a neutrally charged particle, which is neutron. So atomic mass doesn't change because it's capturing a massless particle, which is electron. However, atomic number decreases by 1 because 1 proton is already neutralized by that electron. So generic equation of the electron capture is we have a parent element with atomic mass A and atomic number Z, capture an electron, so the mass will not change, but atomic number will decrease by 1. An example of electron capture reaction is a decay of a nickel 56 into a cobalt 56. So the equation is X with A and Z plus electron with a 0 mass and -1 charge will become a daughter element with the same mass but with atomic number reduced by 1. So nickel with a 5628 will produce a daughter element which is 56 but with 27, and in 27 you see there's a cobalt as an element. And here's a diagram. An electron is captured by nickel 56 and 28 protons end up with 27 protons, but 28 neutrons will end up with 29 neutron, with extra neutron, because as I said, that negative charge of electron will neutralize a positive charge of the proton, making it neutrally charged. That means it is neutral. 1 neutron is formed. Here are some examples of beta decay. Determine the element that is produced when a chromium 46 undergoes beta positive decay and write equation, generic and decay reaction equation. So generic one is the one that you write first, is XAZ undergoes beta positive, and new element is formed, is a daughter element with the same mass but with atomic number which is reduced by 1. So chromium and vanadium is already created. So vanadium 46. Determine the element that is produced when a cerium 141 undergoes beta negative decay and write generic and decay equation. So you do with a generic one, it's a beta negative. So electron is emitted. Now electron is emitted, is negative, so atomic number is increased by 1 while the mass is not changed. So if you see on the periodic table, the praseodymium 141 is formed and electron-like particle is emitted. After a nuclear reaction, such as alpha or beta decay has occurred, the daughter nucleus or a new element that is formed is with a high energy. That's what is called in an excited state. As a result, the nucleus spontaneously releases that extra energy in form of gamma ray in order to return to a lower, more stable energy state. So in a gamma decay reaction, the highly energetic and massless and chargeless photon is emitted from the nucleus. So massless and chargeless. So that means the mass is not changing and charge or number of protons is not changing. So element remain unchanged. However, that energy is released so that element it is in a stable energy level. For example, helium-3 releases that energy in form of gamma ray. So helium releases that gamma energy, emitted the gamma ray energy, release the extra energy, and atomic mass or atomic number does not change. So to indicate that element is in a higher energy level, not in a stable energy level, in a higher energy level, you put an asterisk. And after emitting that extra energy, that is going to be on a stable energy level. Here is a summary of nuclear decay. So alpha emitter is a helium nucleus. New element is formed with a mass reduced by 4 and atomic number reduced by 2. Beta emitter, it is going to be beta positive or beta negative. For beta negative, for example, the new element is formed and mass is the same, but atomic number is +1, is increased by 1. Since that we are here in a beta emitter, in a beta positive, an electron like is emitted, but it's called positron because the charge is +1, not -1. A new element is formed and mass number is the same, but atomic number is reduced by 1. That is the difference between beta positive and beta negative. In a gamma emitter, like a photon is emitted, that extra energy, to make that nucleus in a stable energy level, mass remain the same, atomic number remain the same. Radioactive decays are associated with a certain level of risk. Alpha particles, beta particles, and gamma ray all pose a danger to a living tissue because they can ionize or strip the electrons from atoms. When ionizing radiation makes contact with a living tissue, it can result in burns, tumors, or other harmful effects. Alpha particles have a strong ionizing ability due to their positive charge and high mass, but they are not that harmful because of the short distance they travel. Beta particles and gamma rays are dangerous because they have a greater penetrating rate in the air and they carry a lot of energy as well. Here is a summary of the characteristics of radioactive decays. So alpha decay radiation is alpha particles or in the form of helium nucleus. Electric charge is +2, is like a heavy and very charged particles, but it travels in low distance. Beta negative decay emit the electron like particles, so charge is -1. Beta positive emit similar one, but is a positive charge, it's a +1. Electron capture doesn't emit anything, so no particle is emitted. And gamma decay, charge is 0, is neutrally charged and massless. However, it has a lot of energy. So penetrating is for alpha is 2 to 4 centimeter. For beta is 200 to 300 centimeter, and for gamma is a 500 meter. In tissue depth is a 0.05 millimeter. For beta is 4 to 5 millimeter. For gamma is up to 50 centimeter or more. So can penetrate you through. Shielding, how to protect? You can, from alpha particle, you can protect it with a paper or clothing because that travels slow and in short distances. For beta, you have to have heavy clothing or gloves. And for gamma, you have to have real protection. It's a lead or thick concrete or lead apron, like in an X-ray. If you remember that to go to X-ray and to protect yourself from that exposure from X-ray, you can wear lead apron, and the technician that is doing that X-ray is behind thick concrete wall. It's protected. Typical source of the radiation is radium-226. For beta decay is a carbon-14. We mentioned that it decay into nitrogen. And for gamma technicum, 99M, which is the one actually that we use for thyroid treatment. To conclude this section, we have a summary of penetrating ability of the radioactive decay radiation and how to protect against it. This is section 7.3, half-life. In this section, we're going to talk about half-life. How can we use it to determine the age of the fossils or rocks? Also, how to solve the problems involving half-life. Radioactive decay reactions are spontaneous. There is no way to predict exactly when a particular unstable nucleus will disintegrate. Radioactive materials decay at different rates, which can vary significantly. The average length of time it takes a radioactive material to decay to half of its original mass is called the half-life. For example, iodine-131 decays by a beta emission and associated gamma emission with a physical half-life of 8.04 days. So the original amount, for example, in this case, 20 gram, it will take 8.04 days to go to half of its original mass, which is 8. After 8 days, it's going to be 10 gram. And then after another 8 days, for 16.08, for example, it's going to be half of the 10, which is going to be 5. And then another 8.04 days is going to be half of the 5. That means 2.5. And this will continue. Here is an example. Carbon-15 with a half-life of 2.5 seconds decays to nitrogen-15. Suppose a sample of carbon-15 has an initial mass of 256 milligram. Assume that mass is conserved. Copy and complete the table. So this is a table. Every 2.5 seconds, mass of the carbon-15 is going to be half. And half of the carbon-15 original mass is going to be decayed into a nitrogen-15 every 2.5 seconds. So at the time 0, we have 256 milligram of carbon-15 and 0 milligram of nitrogen-15. Total mass is 256 milligram. After 2.5, which is a half-life, half of the mass is going to decay to a nitrogen-15. So what is left is 128, and what is decayed is 128. But total will remain the same, 256. After another 2.5 seconds, which means at a time 5 seconds, it is going to be half of the 128, which is 64. And another half is going to decay to a nitrogen-15 that will make as a total of 192 nitrogen-15. But together, it's going to be 256. So mass is conserved. Another half after 2.5 seconds is going to be from 64, half is going to be 32. And that 32 is added to a 192 milligram and makes 224 milligram, but total is 256. And this continues. Half of the 32 is a 16. That 32 is joining to a 224, will make 240. And the last one for this example would be 8. And that other 8 is joined to a 240, will make 248. And this will continue, like a 4, 2, and 1, half, etc., etc. So the graph would be pretty much, if you plot the graph, would be something like this. So amount of nitrogen is increasing, and amount of carbon-15 from 256 is half. after 2.5 seconds to a 128. Another 2.5 is half to a 64, and that will continue 32 and 16 and 8, and that will limit to 0 but never becomes 0. This is an illustration how the decay will happen. So mass is going to be half of the original substance, and other mass is going to increase each time that there's a half-life. And you see that different radioactive isotopes will have a different rate of decay, but the process look alike. Let's look at the mathematical model of the half-life. Radioactive decay is an example of an exponential relationship. As time increases, the mass of the radioactive isotope remaining in a sample decreases at the exponential rate. So the mass of the radioactive materials with an initial sample mass of A0 is related to time t and half-life h in this formula. So A is equal to A0, which is the original amount of material, substance, times half in the power of t divided by h, or A is equal to A0, 0.5 in the power of t over h, when t is time and h is half-life. Solving for t or for a half-life, we get this formula using that formula transformation. So we can move A0 to another side of the equation, and that'll become A divided by A0 is equal to 0.5 in power of t over h. And then we'll use a logarithm on both sides of that equation, and we get logarithm of A divided by A0 is equal to t over h times logarithm of 0.5. And then next would be solving for t. That t is equal to h times logarithm of ratio A divided by A0 divided by logarithm of 0.5. And I want to warn you that is logarithm of A over A0 first, and then you can divide it with a logarithm of 0.5, not just A divided by A0 divided by 0.5. So make sure you don't make that mistake. So logarithm of A divided by A0, and you calculate it, divided by logarithm of 0.5. And if you solve for h, you're going to get similar one, is a t times logarithm of 0.5 now, divided by logarithm of A divided by A0. Let's do some practice using those formulas that we just learned. Neon 19 has a half-life of 17.22 seconds. What mass of neon 19 will remain from 100 milligram initial sample after time 30 seconds? So what is given? Initial sample of 100 milligram. Half-life is 17.22 seconds. Time is 30 seconds. What we're looking for is what is remaining from original sample. So we can use formula A is equal A0 times 0.5 in power of t over h, and then we have everything to plug those in a formula. 100 milligram times 0.5 in power of 30 divided by 17.22, and then you can plug those numbers in the calculator, and you can find that the sample that is left is 29.89 milligram, or 29.9, or even you can round it to 30. After 10 years, a 100 milligram sample of argon-42 has decayed to 81 milligram. Estimate the half-life of argon. So what we have here is original sample mass is 100 milligram, time is 10 years, remaining mass is 81 milligram, and half-life is required. So remember that we can calculate for half-life using that formula that we already just learned. H is equal time times logarithm of 0.5 divided by logarithm of ratio A divided by A0. Now we have everything to plug into calculator. So it's 10 years times logarithm of 0.5 divided by logarithm of 81 divided by 100 is 0.81. And then we get half-life is 32.89 years. Or if you can write it, round it, you can write it as 33 years. One of the applications of the half-life is the carbon dating. Half-life of the carbon-14 is 5,730 years. It decays into a nitrogen-14 according to the following nuclear reaction. Carbon-14, 6 undergoes a beta-negative decays and new element is formed as a nitrogen-14. Now the carbon absorbed during the photosynthesis or typically during that carbon cycling, like a food that we take, it is mixture of the carbon-12 and carbon-14. So that mixture is always constant. So ratio of the carbon-14 to carbon-12 is generally constant and equal to all living things because they are part of the carbon cycle when they are part of food chain. Now, when organism is dead, it stops getting carbon-14 and carbon-12, it stops getting food. So that means that carbon-12 will stay the same because it's not radioactive, but carbon-14 will decay. So the mass of the carbon-14 will decrease. As a result, a ratio between carbon-14 to carbon-12 will be decreasing as the organism is dead. So because the carbon-14 is decayed into a nitrogen-14, nitrogen is released into an atmosphere, so the carbon-14 is going to be half every 5,730 years. So scientists look at the fossil and ratio on that fossil between carbon-14 and carbon-12. And based on calculation of that ratio, they'll get into that conclusion, very accurate conclusion, to how long it took for that ratio to be decreased for that certain value. So they can figure out the age when, or a time when that organism actually was alive or it died. So again, scientists use this known rate of decrease to determine when the organism died. So after a certain years or thousands or millions years, the percentage of carbon-14 to carbon-12, it will decrease. And based on that amount of that ratio, you're going to find out when that fossil was alive. So when died, how many years ago it died. So that's a very good and accurate application of the half-life, which is carbon dating. What about to calculate the age of the rocks that pretty much never had any organic material in it, never had life around it? So interstellar rocks can actually calculate the age when they are formed by using aluminum-26 The aluminum-26, for example, has been used to measure the age of interstellar rocks. How does it work? Aluminum-26 decayed into a magnesium-26 with a half-life of approximately 720,000 years. So the percentage of aluminum-26 ratio over a magnesium-26 will give you a very accurate value when that rock is formed, and that will be like a millions or billions years ago. Scientists can approximate the age of the sample by comparing the relative masses of aluminum-26 and magnesium-26 in a similar way as a carbon dating. So as I said, magnesium-26 is going to increase and aluminum is going to decrease. But this ratio is going to depend on a number of years that pass, so it's age that pass. So this is how we can use half-life or decays, radioactive decays, in order to calculate age of the rocks, for example, or age of living organism using the carbon dating. And this is it for section 7.3. Have a good one.